In this section, I am going to give the introduction about a tree data structure. Generally, a data structure is said to be linear only when the element forms a sequence or when it forms a linear list. Previously, we discussed a few linear data structures like arrays, stacks, queues, and linked list we discussed, which organize the data in a linear order. When we say that the data structure is non-linear, means when the elements form a hierarchical classification where the data items appear at various levels like this. If you check here in this example tree, the data all the data elements are appearing at various levels. So it is not in a form of linear order, or it doesn't it doesn't form any linear structure here. That's why we call this trees and graph data structure as a nonlinear data structure, because the trees and graph structures represents the hierarchical relationship between the individual data elements. And trees provide an efficient way of organizing, storing and retrieving the data elements, and we can say that it is a versatile structure which can be used for sorting, searching, indexing and traversal applications. When it comes to the definition of trees and data structures, trees are nothing but it is a nonlinear hierarchical structure which is used to store, organize and retrieve the data in a more organized and a presentable way. And when we take a tree data structure, it consists of nodes. These are each and every circle here represents the nodes. So it consists of the collection of nodes, and all the nodes are connected by the edges. This line indicates the edges which initiates the connection between the nodes, and each representing the data or an object or an information. Each node contains the data or information or the object, anything it can be. So the actual data element can be stored only inside the nodes, and the tree structure is determined only by how the nodes are linked together. The significance of trees in data structures are: it is a fundamental data structure which are used in computer science, and it allows for efficient organization, storage and retrieval of data in more structured format, and it helps the programmers to quickly access the information and traverse a large data set by organizing the data into tree forms. And this tree data structure is very much essential for various algorithms and applications such as searching and sorting and many other applications. And many of these algorithms rely on trees to store the data in an ordered or hierarchical fashion so that they can be accessed efficiently. In addition to searching and sorting algorithms, trees are also used in pathfinding algorithms, mainly such as Dijistra's algorithm. And next topic is about the features and characteristics of tree. The very first feature is hierarchical structure. A tree data structure organizes and stores the data hierarchically, much like a real tree with the branches. If you check this example, yes, it looks like a tree with a different with multiple branches, and it represents the relationship between the different elements as well, which would allow us to understand their connection. And each and every nodes here would be connected by the edges. And the next feature is it has root and leaf node. So here the topmost node in a tree is called a root node. So here the topmost node is A, which is the root node, which is the origin of the node, and it serves as a starting point, and it provides access to all other nodes. If you want to access any other node, only through root node you can traverse. And when it comes to the leaf node, the node which doesn't have any children are called the leaf nodes. If you check here, the node D doesn't have any children, node H, G, I and J doesn't have any children, and these are the leaf nodes, and it represents the end point of the tree branches. So the tree ends with the leaf node. And third feature is flexibility and scalability. The trees can grow and evolve as needed. New nodes and branches can be added to the tree to accommodate the additional data or changes in the tree structure, and this flexibility makes the tree suitable for dynamic and expanding data sets. So if you want to expand the tree, if you want to add more data elements, you can do as many data elements you want to include, that can be included in the tree structure, and it is more flexible and it is very scalable as well. And if you want to do any corrections or any changes in the tree structure, if you want to make also, that can be done easily because it's dynamic. And the next feature is efficient operations. With the help of the tree data structure, we can can perform the operations in a more efficient way. The operations like searching, insertion and deletion, everything can be done in a more efficient way, following because we follow the links between the nodes, and we can quickly navigate through the tree to find the specific data. So when it comes to searching or any other operations, if you want to perform, since we have a connection between each and every nodes, it is very easy to navigate from one node to any other node in a tree structure. And these are the features and characteristics of tree. And the next topic is about the basic terminologies. I am going to discuss the basic, what are all the basic terminologies we use in a tree structure. The very first terminology is a root. Root is nothing but it is a first node. First node is called a root node. Every tree must have first terminology is a root node. Every tree must have a root node. We can say that root node is the origin of tree data structure. If you check this example, the root node is A, which is the origin of the tree structure. In any tree there must be only one root node, and we can never have multiple root nodes in a tree. So if we, in the previous example, if you check, the root node is A, which is the origin of the tree. And the second one is edge. Edge is nothing but the connection, the connecting link between any two nodes is called as a edge. In a tree with n number of nodes, there will be maximum n minus 1 number of edges. So if there are n number of nodes are there in a tree, maximum there would be n minus 1 number of edges in a tree structure. If you check the connection between any node, the connecting link between any two nodes, so A and H are getting connected through this edge, right? So any edge A and C are connected through another edge. So there are edges, right? All the connecting lines we call it as the edges. Only through edges the data elements will be connected. And the next terminology is parent. In a tree data structure, the node which is predecessor of any node is called as a parent node. In simple word, we could say like the node which has a branch from it to any other node is called a parent node. Parent node can also be defined as the node which has child or children, we call it as a parent node. The node which has a child node, we call it as a parent. If you take a root node, the root node is acting as a parent node for the node B, C and H. And then again if you take the B node has again two children D and E, so we can call the node B also as a parent node. So any node which has a children or which has a child, we can call it as a parent node. So if you check here, the parent nodes are B is a parent example node, B has a child node, C also has a child node, H doesn't have a child node, so we cannot call H as a parent node. So B, C, E also has a child node G, F has a children I and J, so B, C, E, F are the parent node. The next terminology is a child node. The child node is nothing but the node which is descendant of any node is called as a child node. In simple words, the node which has a link from its parent node is called as a child node. In a tree, any parent node can have any number of child nodes. So all the nodes except the root node are the child nodes. If you check, this B, C and H are acting as a child node for A. If you take the node D and the node E, it is acting as a child node for the parent B, and E is a child node for the parent C, G is the child node for parent E, I and H are the child nodes for parent F. So any node which has a parent, we call it as a child node. So example, child node for B. Children of I think two nodes are there for the parent B, right? So children of B are D and E. So D and E are the child nodes for the parent B. The next terminology is siblings. Nodes which belong to same parent are called as siblings. In simple word, the nodes with the same parent. What all the nodes, if two more than one nodes are sharing the same parent, means we call those nodes as a sibling nodes. For example, if you take, we will take the parent node B. B has two child nodes D and E. So, we could say that D and E are siblings. Because D and E shares the same parent, so we call it as D and E are siblings. And also if you check B, C, H are also the siblings because it shares same parent A, and I and J are also the siblings for the parent node F. Sorry, since it shares the same parent F. And the next terminology is a leaf node. The node which does not have any child node or the node with 0 degree, we call it as a leaf node. Simple. The node which has no child node, we call it as a leaf node. If you check here, the node D is a leaf node because it does not have any children. F also is a leaf node, I is a leaf node, J is a leaf node, and H is also a leaf node. The node which does not have any children, D, G, I, J, H. These are the leaf nodes. And next terminology is internal nodes. In a tree structure, the node which has at least one child, we call it as an internal node. In simple word, an internal node is a node with at least one child. So, the node which has at least one child, we call it as an internal node. The nodes other than the leaf nodes, also we can say that the nodes other than the other than the leaf nodes are the internal nodes. Why? Because the leaf node does not have any child node. Leaf node is the ending point of the tree structure. So, other than leaf node, all other nodes we can call it as internal nodes. So, the node B, C, E, F are the internal nodes. The node which has at least one child node. And next is in degree, degree, and under degree again there are in degree and out degree for each node. So, the total number of children of a node or the number of subtrees of a node is called a degree of the node. In simple word, degree of a node is nothing but it is the total number of children it has. For example, again under degree there are in degree and out degree. Out degree is nothing but the total number of children the node has. If you take the degree of F, okay, let's check the degree for node F. If you want to check the out degree for node F, out degrees means what? The number of child nodes the so and so node has. If you check the out degree of F is going to be 2. There are two nodes, right? I and H are there. I and H are the children for F node. So, the out degree is 2 and degree is in degree is the parent node, you know, like the from F the number of from where from which parent node it actually comes from is going to be the in degree. So, if you check the out degree, it is going to be 2 and the in degree for the node F, it is going to be 1. Out degree is 2, that is I and J, and when it comes to in degree for the same node F, it is going to be 1 and in degree node is C. So, this is how we are supposed to calculate in degree and out degree for each node. And the next terminology is level. In a tree data structure, the root node is said to be at level 0 and the children of root node are at level 1. Likewise, it would be going, so which means each step from top to bottom. So, always when you compute the level, always we are supposed to start from the root node and always the root node is said to be at level 0. If you check, the root node is at level 0 and this is level 1 and this level is second level and this is level 3. So, the total level of the given example a tree structure is 3. So, always you are supposed to start from level 0, always the root node will be at level 0 only, the children of the root node will be at level 1, then again the children of other nodes which are at level 1, the children of the nodes which are at level 1 will be at level 2 and so on. So, in simple word, in a tree, each step from top to bottom is called as level, and the level count always starts with 0 and incremented by 1 at each level. And the next is, so if you check for the example tree structure, the total number of level it has is 3. And the next one is depth. Depth is nothing but the total number of edges from the root node to your particular node, which is called the depth of the node. In a tree, the total number of edges from the root node to a leaf node in the longest path is said to be the actual depth of the tree. So, in simple words, the highest depth of any leaf node from the root node is called as the depth of the tree. So, here the depth of, let us check the depth of the tree. The highest depth of any leaf node in a tree. So, all these 3 leaf nodes are at the same level. So, the depth of the tree is going to be the total number of edges. So, depth here is 3. The highest depth of the given tree is 3, which means the total number of edges. And next is path. The sequence of nodes and edges from one node to another node is called as a path between any two nodes. It is going to be, so the one node to another node, if you want to traverse, like through some path only we would be traversing it, right. So, that we call it as a path. If you want to traverse from one node to particular node, through which are all the edges you are traversing, all those we consider it as a path. So, the length of the path is the total number of nodes in that path, that is going to be the length. For example, we calculate the path, okay, to reach from A to G. If you check, A to B is A to B, then again B to E we have to traverse, then again E to G we need to traverse. So, to traverse from A to G, the path is going to be A to B to E to G. This is the path, and the length of the path is going to be total number of nodes in that path. So, the length of the path here is 1, 2, 3, 4. So, totally 4 nodes we have visited to reach so and so node. So, the length of the path is going to be 4 to reach from A to G. Source node here is A and the destination node here is D, and this is the length of the path, and the path is nothing but the sequence of the nodes and edges from one node to another node. And next one is a subtree. So, each node from a node forms a subtree here recursively. So, every child node will form a subtree on its parent node. If you check here, let me change the color. Okay. If you take the parent node A, it has two different subtrees, it has 3 subtree. One is this subtree number 1 is this one, and this is another subtree, and this H is another subtree. And again, if you take the node B, B has again 2 different subtrees. One is subtree number 1 is this one, subtree number 2 is this one. Then again, if you take C, there is only one subtree through F. This is what the subtree is. So, every child node, each child node in a tree structure can form a subtree recursively. So, every child node will form a subtree here on its parent node. So, every parent node, if you take, it has subtree, depends upon how many number of children it has. If it has 2 child node, it would have only exactly 2 subtree only. If it has only 1 children, only 1 subtree it could generate. If you take the node C, it has only 1 child node, which is F. So, through F it can form one complete subtree. So, C has only 1 subtree, but under B there are 2 subtrees possible because it has 2 child nodes, and if you take H, there is no child node, which is a leaf node. So, it does not come under a subtree only actually, because it has only 1 node. So, it depends upon the subtree can be formed based on the number of the child node the individual parent has. So, these are the basic terminologies. In the next video, let me discuss the types of trees and its applications.